Hey everyone. Today we're going to go over the concept of half-life. Now, half-life is a property of radioactive nuclei that refers to the amount of time it takes for half of the radioactive sample to become stable, which means it's the amount of time for half of the atoms that are radioactive to decay and undergo radioactive decay. The tricky thing with half-life is that people usually kind of think when they're first learning this that it involves a specific quantity of the radioactive sample. But no, it's really just a measure of time for half of the sample to no longer be radioactive, which means that half of it has become stable. Now, half-life is a unique property to different radioactive nuclei. It is something very dependent on the stability of the nucleus, and as you can see here, it is just a measure of time and will vary with each radioactive nucleus. The more stable the radioactive nucleus is, the longer the half-life is going to be. So you'll have longer and extended periods of time between radioactive decay uh, for radioactive nuclei if there is a longer half-life. A shorter half-life refers to a more unstable nucleus that is undergoing rapid radioactive decay, and so they're releasing radiation at a much faster rate than, let's say, other nuclei might as well. Here we can see an example of half-life, just actually visually taking a look at the atoms. So we can see at the very beginning with 0 half-lives, okay, all of our atoms are radioactive. After a single half-life, only half of the atoms are radioactive. And then after a second half-life, we get half of the half. So about a quarter of our radioactive atoms are still remaining. So when graphing a plot of half-life, we can actually see that for every single half-life that occurs, it's always the initial amount of the previous half-life being divided by 2, or rather being taken half of. So when we have an initial starting quantity at time equals 0, the first half-life would have half of the remaining. At the second half-life, we would have a quarter of the remaining because we're taking half of a half. At a third half-life, we would have 1/8 of the remaining sample of the original, sorry, because we're taking half of a half of a half and so forth. So as we continue going through our half-lives, we just keep halving the quantity and it just becomes a smaller and smaller fraction of that original sample. And just one more visual here, just showing these quantities of radioactive nuclei decaying in relation to the half-lives. So every half-life, we are just really halving the quantity of our radioactive nuclei. The duration of the half-life would vary depending on what that radioactive nucleus is, but the idea remains the same, that we just keep taking half of what we had before. An example where we see half-life used in everyday life comes from radon-222. This is a radioactive gas that is more known to homeowners and people who have to undergo just house inspections and keeping track of this radioactive gas that does build up in certain parts of land from the decay series of uranium-233. It's a naturally occurring radioactive gas that's a product of radioactive decay from radium, which extends further down the uranium series. Radon-222 is a colorless and odorless gas that will sometimes build up in the home. And due to the fact that it's radioactive, it is a large cause of health concerns, and it's actually one of the leading causes of lung cancer in both smokers and non-smokers to people who have been exposed to long periods of time. Now, radon has a half-life of 3.8 days, and this is something that is taken into account when measuring the amount of radon-222 within a home. This is something that house inspections have to usually go through, and homeowners have to be aware of and constantly measure um, in order to make sure that the radon levels in their home are not exceeding a certain threshold, because this can pose very, very serious health risks. Another example of where half-life is used is in carbon dating. Now, all living things have the radioisotope carbon-14 within their system. This is a radioisotope that was first created through the exposure of gamma radiation onto nitrogen-14 in the atmosphere, which eventually created a form of carbon dioxide containing the carbon-14 isotope. Plants consume this isotope, and then it gets passed on to other living organisms, and it's just embedded in our chemical makeup. Now, this radioisotope has a half-life of 5,730 years. And so when measuring the age of artifacts and things just found in the Earth that were once living, it's actually possible to identify how long ago they existed by measuring the amount of carbon-14 still remaining. So carbon-14 is a very common practice or a very common isotope used for the practice of carbon dating to figure out how the age of objects through the half-life of this radioisotope. Now, suppose we want to work with how exactly do we calculate things with carbon-14? Well, let's look at an example. Suppose a house is found to contain 100 grams of radon-222 within it. How much time must pass for there to only be 12.5 grams of radon remaining? So if we have 100 grams of radon-222, after the first half-life, which we mentioned before was 3.8 days, well, we'd have half of that 100, which would be only 50 grams remaining. After a second half-life, which means an additional 3.8 days, so we are 7.6 days from the start time, you would have half of that half, so only 25 grams. After a third half-life, and again another 3.8 days, we now have half of the half of the half, so half of 25 puts us at 12.5 grams. This would put us at 11.4 days after the initial reading of this radon 222. So the half-life remains constant. It is 3.8 days, and every 3.8 days, our quantity is being halved until we only have 12.5 grams remaining. So to answer this question, it would take approximately 11.4 days for there to be 12.5 grams of radon remaining. Now, as half-lives continue to pass, we will continue approaching zero, but we're never actually going to reach zero in terms of the amount of radioactive substance remaining. Let's look at another example. Phosphorus 32 has a half-life of 14.3 days. How many grams of phosphorus 32 remain after 57.2 days if you start with a 4 grams of the isotope? So if the half-life of this radioisotope is 14.3 days, after 57.2 days, we would have 4 half-lives occur. So this radioactive isotope would have decayed 4 times. During the first half-life, if we start with 4 grams, then we would have half of that remaining quantity, so just 2 grams. We've established that 4 half-lives are going to pass over this 57.2 day period. So after 14.3 days, or 1 half-life, we're now down to 2. After a second half-life, we would have half of that, so only 1. After a third half-life, we would have half of that, and so we'd have 0.5 grams remaining. And after our fourth half-life, we would have half of that, which would be a quarter of a gram or 0.25 grams. So after 4 half-lives, we would have 1/4 of a gram remaining or 0.25 grams. So rather than looking at the problem in the way that we approached it before, where we were taking each half-life and just dividing the quantity by 2, we could actually rewrite this in a longer expression, really working more so with an actual equation. Since dividing by 2 is the same as multiplying by a half, and we divided by 2 4 times, this would be equivalent to rewriting our work as taking 4 grams times a half 4 times. When we condense our expression here, we get 4 grams times a half to the power of 4, since 1/2 was multiplied by itself 4 times. That number 4 in the exponent refers to the number of half-lives that have occurred. So we are seeing here that there is a way to express the number of half-lives and the starting quantity within an actual expression. Now, these numbers are for that one problem. If we actually take what these numbers are representing, those 4 grams being the starting amount, that exponent of 4 being the number of half-lives, and our final quantity of 1/4 gram being the remaining amount, we can replace these with more general variables, and we have right here our half-life equation, where A of t, the amount after a certain time period t, is equal to A of 0, which would be the initial amount, divided by 2 to the power of n, where n represents the number of half-lives, and the number of half-lives can be expressed as the time elapsed, or the amount of time that has passed, divided by the time of a single half-life. So this right here gives us an equation to use in order to calculate either the final amount, the starting amount, the number of half-lives, the time elapsed, or even the duration and the time of a single half-life.